This will be my last video. After that, I won't be able to do anything. So in the whole mechanics, few special points I would like to cover here. First is this virtual work method for the constraint problems, and also remember the angular velocity of the line formula and the velocity of separation or velocity of approach, and that acceleration can be written as vx dv by dx. Here this is not total velocity, it is the velocity along a particular direction like dx, or if it is dx then it is the velocity along the x direction. If it is dy then it is the velocity along the y direction. But if I want to write, because we cannot divide by the vector quantity, that's why I am taking only a particular direction displacement. But if I write this in this form, then I can take the total vector, which is v dot dv is equal to a dot ds. But if I take the ds here in the denominator, which is a vector, it is not possible to take the vector. That's why we take only dx, dy or dz in the denominator, not the total vector. And also the radius of curvature formulas we should remember. RC is equal to 1 by 2a, 1 by 2 times of coefficient of the x square in this parabola. And in this case of ellipse, this smaller circle will have smaller radius, and that would be given by the smaller length b divided by the larger length square, which is this b by a square. And for this larger radius RC, we have to take the larger length, my major axis length a, divided by the smaller length square, a by b square. It is not, it is by a by b square, it is b by a square. And if the ellipse is moving and a particle follows the ellipse, a particle is moving in this ellipse path and the ellipse starts moving, then we have to go to the ellipse frame, because the radius of curvature we use in this formula for the a perpendicular is equal to v naught square by rc. We have to take, it is the radius of curvature of the actual path. Means if the body is moving in a circle and the circle is at rest, then the body is having the actual path. This is the actual path of the body, point P, let's say, and it would be having the radius of curvature r. But if this circle starts moving, the point P will start moving in this manner. So if it starts moving in this manner, the radius of curvature will not be r in this case. So in the ground frame, the radius of curvature would be something different, but we have to, which is very complicated to tell. So that's why we will go to the ground frame, sorry, we will go to the circles frame. And in that case, the radius, the path will be simply a circle in the circle frame, and the particle's velocity will become different now in this frame, and we have to put the velocity of the object in that frame, and radius, that is v in the frame square divided by the radius in the frame, that is equal to a perpendicular. And this a perpendicular is the force in this same frame. Means these are all dependent on the frame. Now in the projectile motion, we have this equation, this 1 plus tan square theta can be written as cos square theta in the denominator, and this whole can be written in this form also. And this is for the projectile motion, where this r is the range along the horizontal line. Means if the particle is thrown from this point in this direction, and let's say this is the height, it is thrown at height h, then the range will be taken, the range r here, this is the length along this horizontal line, not the total range. Total range would be equal to this, but here in this equation we have to take this horizontal plane range only. Now in the case of safety parabola, we should remember this formula for the minimum velocity and maximum displacements. V is equal to under root of g bracket the height y into y plus root of x square plus y square, and the angle at which we have to throw so to reach the maximum position, extreme position in the trajectory possible, that would be given by this v square by gx. So maximum angle v square by gx, v is not square by gx g. So along with your revision, I will also do my revision. So I will write down v is equal to the square root z times bracket y vertical height into root of x square plus y square, and also the tan theta of the throw is equal to v naught square by gx naught. Okay, now moving ahead, height is given by this time of flight. Whenever the object is thrown up or it is dropped, the height change, the height traveled. If it is dropped and it reaches this ground with a velocity v, and or if it is thrown with a velocity v, it reaches the top point, maximum height, where its velocity will become 0. This is the height h. Then in this case, the time of flight, in this, the time here would be t taken for this journey, and time would be same here, t, and that would be given by this 2h by g root, and the velocity will be related to this h with this equation. And one more important equation: when the projectile is thrown along on the slope where the slope is having some beta angle, and from the slope we are throwing at some alpha angle up the slope, or with beta angle down the slope. So in this case, when we are using this up the slope, we have these formulas. Height is again given by the v perpendicular square divided by 2g perpendicular, and the time of flight would be again given by the same formulas. Total time of flight is 2 times of v perpendicular by g perpendicular. Means it will take some time to go to the reach this height at this slope, which is h, and then it will go down. And the range, this range length covered in this upward slope, means if it is thrown upward, then the range, because the projectile would look like this, and in this case the range, this r length would be equal to this v perpendicular would remain same. We get 2 times of v perpendicular into, but v parallel is not here. Instead of v parallel, we get v times of cos alpha plus beta in the upward slope through divided by the g perpendicular cos of beta. And the range is maximum when the alpha is equal to pi by 4 minus beta by 2. This is the case when the throw is upward, and this becomes positive when the throw is downward the slope. And this also relates to the horizontal throw, means if I throw from the horizontal plane with an angle alpha, the maximum range occurs at the 45 degree. Similarly here, the maximum range is occurring at 45 degree minus beta by 2. In this case of ground, the beta is 0, so we get pi by 4. So this formula can be memorized, and this is also important for projectile. And the maximum range occurs at this, and if we put this value, we will get the equation of r to be equal to simply v square by g times 1 plus sine of beta. In the upward slope, the distance is lesser, but if I throw at downward, the range can be larger. And in this case, when the throw is upward up the slope, we get a positive sign here for the maximum range, and in the r maximum for the downward slope, we get a negative sign here. So these circled signs will get changed if we throw down the slope. Here it is talking about the upslope only. Now a rotating vector has the d a cap by dt is equal to omega cross a cap, and for any circular motion, the minimum velocity required if the object is made to move in a circular path by any rod or any groove path, then in that case, means if there is no restriction, okay, let's say an object is moving in any ring, and let's say it is a bed with a hole and it is moving in the circular path, so there is no limit of the tension required by the body. It can always follow this circular path. So in this case, the minimum velocity required at this point to reach this top point will be given by simply conservation of energy. The energy should become 0 here, so the velocity here would be equal to root of 4gr. This is radius r, so the v is equal to v naught is equal to root 4gr at this point, so that it completes the circle. But instead, if I take a hoop and a bodies moved with the velocity v, but in this case this body needs a centripetal force in this case, because the normal force cannot act on this in the upward direction, means in the outward direction the normal force cannot act. There is a need of one more thing, that it should not lose contact with the hoop. And let's say if at any stage the centripetal force becomes larger than the the larger than the force required for it to move in this circle of radius r, then in that case it will start following a parabolic motion. So to make sure that it can complete the circular motion, we need to make sure the tension or the normal force here in this case does not become zero at any point here. Means it should become zero at this point only. If it is a hoop, the normal force should become zero at this point only, or if it is connected with a string, the tension should become zero at this point only. It should not slack between path. So for this case, the minimum velocity required is given by under root of 5gr. So depending on the cases, we can find the minimum velocity from these equations. And now there is one more question. This is a rope is wound around a cylinder, let's say, and it has some friction. The string has some friction, and if I pull the string from one side, let's say this is cylinder, and around it I have wrapped a rope of with some, let's say it is massless rope, but it has some friction. So the tension will apply some force in this string, and let's say at any, let's say I'm taking the view from this side of the cylinder, and this is the string wound around it. At any point, let's say here, the tension at one side is T, and due to friction, let's say there is some friction in it, and the other side will get some T plus dt tension. Due to this friction, let's say friction is acting in this direction and it is pulling in this direction, so the dt is the tension at this side more than this side. In this case, because this is a curved path and this is, let's say, t theta angle, then this will apply some force in this direction, which is called the normal force. That would be equal to t theta in this case. And this normal force into the mu, that gives us the f max. And the because these are very small length elements, they are providing very small amount of frictions. This is dn, actually dn, which is a very small force, and each of these elements are providing very small force. So if I pull it with some force, let's say tension T from this side, T plus dt, then this other side, because I am providing a finite amount of tension, the tension cannot be completely cancelled by this small amount of friction. So this friction will reach its peak value, then the element behind it, the length behind it, will apply some friction and it will reach its peak value, then the length behind it will reach its peak value, and similarly all the lengths will reach their peak value. So all of the elements are providing dn into mu friction, which is their limiting friction, and this limiting friction will act as long as there is a point where the friction, the normal force, becomes zero. Means this friction force will be reaching its limiting values at each element, at each point, as long as the normal force does not become zero. Means as long as the tension does not become zero, the frictions will reach their maximum value. And let's say in a given case, the friction does not become zero in this path, and then in that case, let's say other end has some T1 tension and this end has T2 tension. Then if I rotate from one point which is at T2 tension and I go to other side which is at T1 tension, let's ignore this. If this cylinder is wound with a rope and I am rotating about theta angle, and this is, let's say, T2 tension at this side and this is T1 tension at this side. Let's say the T2 is greater than T1, then in that case we get T2 is equal to T1 into e to the power integration of mu d theta. So mu is the coefficient of static friction. We can mu s here, that is mu s d theta integration gone from 0 to theta. So we have to take from this 0 angle to theta and we'll get this 2t is equal to, means if the higher value is t2 and we are getting like this, then we have to put the higher angle at this side and lower at this side, so to make sure that this value is greater than t1. Now along the slope, this is also one more important question, that doesn't matter at which slope you are ascending. If you are on this slope and you are applying some force f at some alpha angle with this slope, then this minimum force required for it to slip upward, the minimum force F required, let's say this is gravity, and the minimum force required for it to slip upward, sorry, in the upward direction along the slope, where alpha is the angle with the slope, that is independent of beta, and that alpha is given by simply mu s of this friction here. Friction coefficient here is mu s. So that tan alpha is equal to mu s, for that is the minimum value for it to slip, and as the alpha becomes greater, this starts slipping. Sorry, this is the case for the minimum force required for it to slip. So at this angle the force is minimum for it to slip. So it does not mean that if you apply force at any other angle it will slip. No, it will not slip, because that is the minimum, sorry, that is the angle at which the force is minimum. So F minimum occurs at this angle, so changing the angle will not make it slip if the force minimum is applied. And there is another case in which we have a slope, let's say beta angle, and on this slope we have a mass m here in this gravity. In this case, if the slope is changed, this will start slipping, and this slipping will occur when this tan beta is greater than or equal to tan mu s. Means it will slip when the tan beta is equal to mu s or greater than mu s. Means that slipping will only occur after you cross this value of beta, while in this case the force minimum occurs at this angle. And in case of, this is for the blocks, this is the for blocks, and this is also for the block. But if we have any body which can roll, then for that body we have this formula, tan of theta should be, sorry, tan of beta, this is beta angle, tan of beta should be greater than or equal to this mu s times the moment of inertia about this body, about the center of mass, that is ICM, plus the, this length is, let's say, r, then we get mr square divided by this ICM again. So that's for the bodies which can rotate. Now there is this case of rope in which if we have one end of, let's say there is a surface here, and a rope is resting on the surface, and here on this side I'm applying T2 force and T1 force here, and this system is now released from the v is equal to 0 initially. Initial velocity at each point of the body is 0, and from the rest I am releasing this body. It has some lambda uniform mass density, and total length is L of this rope is length L. Then in that case, let's say I'm pulling in this direction, and this height is y2 and this height is y1. So if I'm pulling in this direction, I have to take T2 minus T1 if I'm concentrating this acceleration in this direction. This force pulls it in this direction, plus the gravity also applies force in this direction, which is equivalent to this y1 minus y2 into this, sorry, lambda g, and that would be equal to lambda L acceleration of this body along the slope, this surface. And this pulley system can be simply taken as this mass of active single body, which is given by 4m1 m2 divided by m1 plus m2, and the acceleration of this body would be simply equal to the acceleration of the pulley itself, and force by any moving mass dm by dt, that is equal to dm by dt vrel. And also one more thing in this case is that if we are considering any kind of collision case, then in that case the, let's say if any mass dm is coming, and this is the system of mass m, and that mass is getting added to this system, or maybe let's say getting removed from the system, then in that case the force applied by this dm mass is given by this dm divided by the time taken for the dm mass to add, and the relative velocity. If it is going to attach with this mass, then we have to take the initial relative velocity, and if the mass is getting divided, means if the mass is getting removed from the system, then we have to take the final relative velocity, because the initial would be 0 relatively because they are joined, and if the mass is getting attached, and after attachment the velocity relatively will become 0, so it does not make any sense to use that velocity. We have to take the initial velocity in the case of bodies getting collided and stick together, and if the bodies are getting separated, we have to take the final relative velocity here, and this is the mass added or removed divided by the time taken. We have to take sine of dm by dt also, and that is the force due to this dm by dt, and that force is taken on this whole system on dm plus m. This force is acting on this, acts on m plus dm plus m. If this dm mass is very small, then in that case we can kind of ignore the dm and say that the whole force is acting on the m mass. But if the dm mass is large enough, we have to take the force also. For example, let's say there is a gun, and relative to the gun, the bullet is fired with a velocity, let's say v naught, and the bullet is having some mass, let's say 2m, and the mass of the gun is, let's say the total mass of the bullet initially was 80m, and including the bullet, the mass of the gun was 80m, but after the bullet gets removed, its mass becomes 78, and relative to the gun, the bullet speed is v naught. So we can say that, let's say this bullet is from the system, it is getting removed, and in that case we have to find the velocity of this mass after the fire related to the ground of this bullet, of this gun. In this case, the force due to this mass getting released on these two systems would be equal to, F is equal to this mass, let's say it takes t time to get removed, so we get 2m gas getting removed from the system, we get minus 2m by t multiplied by the relative velocity is equal to v naught in this direction. So the total force would be in this direction, and we have to take, this is the actually average force in that time interval, and average force into the total time is equal to the total change in the momentum, sorry, the average force divided by the total mass. Here we have to take the total mass of the system, F average divided by the ATM, that gives the acceleration average, and from this we can say that here actually we are trying to calculate the acceleration of this whole system, but when we have to calculate this force, we are taking as acting on this body, but we have to include the mass of the body, because during the collision the mass may also be the part of the system, and in this case we have to add the mass also in this total mass, so the total mass becomes 80. So we get 2m v naught by 80 t, that is equal to the total acceleration, which is in this direction because of this minus sign. So we get mv naught by 40t, that is the acceleration in this direction, average, that is the average value, and the average acceleration into the time is equal to the total change in the velocity of this gun. So we get mv naught by 40, which is the average, and multiplied by the time, that gives the total change in velocity. Initially the velocity was 0, so with respect to the ground, the velocity becomes mv naught by, also it was m here, so we get v naught by 40 velocity of this gun in this direction when this mass is moving with some v naught velocity in this relatively to the gun. So what I'm saying is that we have to include this mass m also, even though we are taking this force to be acting on this gun, but this force is taken to be acting on this gun, but this mass dm is also taken as part of the body, or we can say that acts on m, but dm is taken part of system, means that small amount of mass will be taken as some part of the system, but it's a dm mass can be ignored if it is very small, but if it is large enough, then we cannot ignore it, and we have to add it in the total mass here in the calculation of acceleration average of this gun. This was for the gun. So moving ahead, we have these equations. Kinetic energy of any rigid body is given by, this is for the rigid body, mvcm square by 2 icm omega net, icm omega net and omega net square, sorry, parallel to omega net. So in this case, let's say there is a body here, its center of mass is this, and this center of mass is moving with some velocity vcm, so it will have some kinetic energy. Total kinetic energy would be given by this mvcm square by 2. Now let's say this body is also rotating in this direction, so I have to take an axis that is parallel to the axis of this omega that is passing through this center, means this axis, and through this axis, this is I through this axis I have to take ICM parallel to this omega net squared, sorry, omega net squared divided by 2. That will give me the total rotational part of the energy. Now let's say if there was any, let's say a cylinder which was rolling on the surface, then in that case if the cylinder is rolling on the surface, its IOR will be this axis, and we have to find the total. This MVCM square can be simply given by the same velocity of the center of mass into MVCM square by 2, and the rotational part will be given by, because this is the IOR, this is the omega net, and we have to, let's say this is the center of mass, then we have to take a axis that is parallel to this center of mass, and about that axis we have to calculate the moment of inertia, and then we can take omega net square, that is this omega squared into I about this axis divided by 2. That's how we calculate. Now okay, what is called a conservative force? A conservative force is a force that only depends on the position, and it does not depend on the velocity or anything else. Also, one more thing, that when we have any cylindrical region of magnetic field and the magnetic field is changing in this region, it will induce electric fields in this medium, in this circular loops. And because the in this circular loops, if we sit at this point and if we take a round, if I put an object here and I release it, the object will move from this point and go round and come back here. But in this case, the kinetic energy of the body will be released, means of the charge will be released, increased, because of this motion in this electric field, and it comes back to the same point, its energy is increased. So that's why this is called non-conservative, because the energy is keeps changing at the points. Means in the conservative force, the potential energy kind of is, in case of conservative forces, we know that total mechanical energy is constant, and in this case the particle keeps on rotating and its energy gets increased again and again throughout this motion. So that's why it is non-conservative force, because the total mechanical energy is not conserved due to this force field providing energy. Now we can use alpha for this torque and motion. In pure rolling, omega r is equal to VCM, and one more important thing is alpha r is equal to ACM. For slipping, omega r is not equal to VCM, but this can be equal in some cases only, where this r is not the radius, but it is the distance from the surface to the center of mass given here. And center of mass is a very important concept which is used in many used in many questions. And the collisions, if the surface is frictionless, the angle of incidence is equal to angle of reflection. This is for the offset maximum. Collision question solving, we get a question of linear momentum conservation, angular momentum conservation, and we can use the definition of E. Instead of using the kinetic energy conservation, we can also use the definition of E if we like to. In some cases, kinetic energy is not conserved when if E is unequal to 1, the kinetic energy is not conserved, and in that case we have to use the definition of E. But if the E is equal to 1, then we can simply use the E is equal to 1, or we can also use the kinetic energy conservation when it is applicable. IOR concept. In IOR concept, one more thing, IOR can tell a tangential but not a radial. The IOR axis, this cannot tell the radial acceleration, because the IOR is not related to the actual path of the object. It is only dependent on the instantaneous path of the object. So in this case, that is only useful for telling the A tangential, but it cannot tell the A radial, which depends on the path or the radius of curvature. Now again, F is equal to ma is used when the mass is constant, tau is equal to I alpha used when the I is constant. If the I is changing, then if the torque is 0 and I is changing, the alpha can still change, because the DL is 0, then I1 omega 1 is equal to I2 omega 2. In cycloid path, motion of a point in RBD is a cyclic path. Let's say a circular disc is here rolling on the it is rolling on the surface, then any point on the body will be following a path which is called cycloid, which looks like this. And the extreme point on the points on the circumference follow this path, and the distance traveled by the point on the circumference. So in this case, this point P by point on circumference. A point on circumference travels eta distance in one complete rotation of the body. And this displacement of this object goes this distance. Sorry. The velocity of the object at any angle theta, let's say it is making theta angle with it. So in this case, the velocity of the object is given by this equation VPO with respect to the ground frame O. The velocity of the point P is given by this 2 times of VC sin theta by 2. Here it is purely rolling body. And this is the theta angle measured with this vertical axis from the downward side. Okay. And one more important thing of the questions is this one, that if we provide any impulse instantly or simply in general the questions when say that impulse is provided, then we say that the omega and we are changed, but the body did not move, the displacement is zero. The body, if I provide some impulse to it, the body will still remain same, but the body will gain some omega and velocity at that instant. Means it will be having some acceleration and some alpha throughout this collision, but it will not make any displacement because the time is tending to zero, and we take almost the displacement of the body to be tending to zero. So only the omega and v is gained by the body, and this frame of the body is also non-inertial because it is having some acceleration and alpha. So now also in case of bodies, rigid bodies, the center of mass is the point where if you sit on the translating frame of the center of mass, the torque about the center of mass due to the pseudo force of the acceleration of the center of mass will be zero on this body. That's why we generally take the frame of the center of mass. Now comes our 12th class. Okay, now let's revise the 12th formulas, 12th physics. So first of all, the constant K used in the electric field is K, which is equal to 9 into 10 to the power 9. Magnetic field, it is 10 to the power minus 7, and that value is for the vacuum only. If we are using any medium, then the K would be changed, and that's why I used a K naught sign here for the vacuum. And for general medium we are using capital K, and for the dielectric we are using small k. And for a parallel plate capacitor, this K is given by C by C naught, and that is also equal to epsilon by epsilon naught. For air it is 1.005 dielectric constant, and for water it is 80. So the K is given by this mu naught. Here K naught is given by 1.4 pi epsilon naught, and in this case this K is given by mu naught by 4 pi. Means the mu naught and epsilon naught are just reciprocal in the reciprocal positions. Means one it is at denominator and one is at numerator. And this 4 pi comes from the symmetry of the surface area, which is given by 4 pi r square for the sphere. From that this 4 pi term comes. Now talking about the polarization in the, if some electric field is provided in a dielectric, it gets polarized and provides, means dipoles are formed in the medium, and the total dipole moment divided by the volume, that is actually equal to the sigma p charge density. Means if I have a medium here and I provide some electric field to it, then these ends will be having some sigma p charge polarized and minus sigma p at this side, and inside I will also get sigma minus p, sigma plus p, but they are consecutive plus minus, so they all cancel out, and overall we get sigma p at this end, sigma p minus at this end. And that's why this total dipole moment, which is given by this sigma p into area, that is the total charge, into this length, let's say L, divided by the total volume, that gives sigma p. So and that polarization is equal to psi into epsilon naught, sorry, electric field provided external. So polarization is equal to psi e into external electric field provided, where this psi e is equal to epsilon naught bracket k minus 1, where this psi e is actually meaning the absolute value of the permittivity increased as compared to the permittivity of the vacuum. So epsilon naught is the vacuum permittivity and epsilon naught k is the permittivity of the medium. So the difference is called this xi. But in case of magnetic field, the xi b or the xi b or the xi used, that is little different. That is relative value, not the absolute value. For example, here we are using epsilon naught times k minus 1, but in the case of magnetic field we use mu r minus 1. If I multiply it by the mu naught, that becomes absolute value, but it is a relative value in this case of magnetic field. Why are they using different for this? I don't know, but they are using it. So just memorize that this is formula for this. Polarization is displacement. Electric displacement is given by the epsilon naught k into electric field. Here, anywhere in this notes, if I am writing epsilon naught, then we should remember that we have to use only epsilon naught. And if I am writing epsilon, then it means the medium effect is counted in it, and medium can affect it. So it can, here this is the absolute formula. We cannot replace this epsilon with e, or we can do by combining this k with e, because that is the dielectric constant. So d is equal to epsilon naught k into a vector, or we can simply say e epsilon into electric field provided, that is called the dielectric constant. And this dielectric constant, I don't know what is used for, so we should remember this formula. This is for the field and dipole moment. And the magnetization is just like polarization. We have the formula for magnetization, and the magnetization looks like this psi into h vector, where this h vector is the external magnetic field divided by the mu naught. So the external magnetic field divided by the mu naught, that is equal to the h, that is called the intensity, magnetic intensity or whatever. And this magnetic field b is also called the, what it is called, forgot. This magnetization is also given by the net magnetic moment divided by the volume. And the magnetization, the magnetic field produced by the medium due to the magnetization, that is equal to this psi into v naught. And these two formulas we should memorize. And then the magnetization, the pm, magnetic field provided by the medium, that is equal to mu naught times this psi into h, which is simply equal to mu naught into the magnetization. So psi h is equal to magnetization. Polarization is psi e into the e naught, while magnetization is psi v into h, where this h can be written as b by mu, b naught by mu. And that's it. This magnetization, if multiplied by the mu naught, that gives me the magnetic field in the medium due to the medium, and the total magnetic field will be given by this mu r into v naught, which is the sum of the b naught and the bm. And in a paramagnetic material with change in temperature, the psi value, which is called the magnetic susceptibility, that changes with this relation, this where this c is called Curie constant. And for ferromagnetic material, the equation looks like this: for temperature greater than the Curie temperature, which is kind of critical temperature, at which after which the ferromagnet behaves like a paramagnet. And dipole makes field outside the axis means, let's say we have a minus q charge here and a plus q charge here, then this field will make this charge will make fields like this, and inside the field will have some opposite direction. So outside this field along this axis, the field is given by this formula, 2 times of this rkp by r square minus a square. We have to remember this r 2 times of kp vector divided by r square minus a square whole square, where it is in the direction of the moment dipole moment vector, while in the equatorial plane we get minus kp vector, and this 2r gets removed. We get r square plus a square to the power 3 by 2. And for large distance this a can be eliminated, and for the field inside we can calculate it, but it is different equation as compared to this equation. We cannot use the electric field equation of the outside for this inner side. I didn't write its formula, but we can calculate it also. And also a dipole moment vector is like any other vector. Any vector can be taken component in any direction, broken down into components. For example, let's say I have to find, let's say there is a very small dipole here, and at an angle theta at distance r vector there is a point P here, and I have to find the field due to this dipole at this point. So it is, I don't have any direct formula for the field at this point, but if I break this dipole into two parts, one in this direction and one perpendicular to it, then these two dipole moment vector P1 and P2, I can use the axis formula and the equatorial plane formula to get the electric field at this point, and I can add the fields due to these two at this point to get an E net value. And this angle theta, this tan theta, half of tan theta is equal to this angle alpha made with this E net vector along this line, which is alpha. Tan alpha is equal to half of tan theta. And one more thing, in this case the dipole moment vector can be taken into, we can take the component of the dipole moment vector, but that thing we can do only when the dipole moment is very small as compared to the length, because if the length becomes finite then the a becomes significant. Yes, if the length is very small, the distance is very small, the a becomes significant, and in that case the length of the dipole we have to consider, and it would be a complicated condition here, because we don't know what, we only know the magnitude of the dipole moment vector, but the dipole moment is given by the q into 2a, that is the 2a is the length, and the dipole moment can be given by any product of 2a and q. So how can we decide what is the length and what is the charge? That would be a questionable thing. So that's why we are using this method for large distance only, so that this a can be ignored. Now the magnetic moment, just like this electric dipole, the magnetic monopole does not exist. The magnetic monopole does not exist, but we can treat the bar magnet just like this minus q and plus q charge field, because this bar magnet forms the same field as the field formed by the dipole, but one difference is that in the magnetic field the field inside is in the same sense as outside, but in the electric dipole the field is in opposite direction inside. So we cannot use the qm charge method for the field inside the magnet, but we can use it for the field outside the magnet, and we can use the dipole moment m is equal to total length into qm m. And also in this case, one more thing, that if we have a bar magnet of total length L, then the charge will be located here at minus qm and qm, and their length would be L, and L should be smaller than L. That is one more thing. And for the bar magnet, and solenoid can also be treated like this, but this is for the field outside only, and the formula for the field is just like this two formulas. And the magnetic moment can also be given by this formula, A into I, area vector into current for any current carrying coil, and if the number of turns is n, we have to multiply it by the n. Or we can say that the area of one coil is, one loop is A, and total n loops are there, so we get total A net is equal to this, means that is effective area vector we have to use. And one more thing, that if we have any loop like this, let's say in this shape, and it is folded in these two planes are, let's say, perpendicular, and the current is flowing in this sense, and current I flowing in it, then in this case if I have to calculate the angular moment, magnetic moment of this coil, so we can easily do this by simply assuming, because this formula is for a flat plane of loop, so we have to take one current in this direction and one current in this direction, so we will complete one loop here and one loop will complete here. That's what I'm saying here. And this will give some moment in this direction, and this will give some moment sorry, this will give moment in this direction m1, and will give some moment in this direction m2. So adding these two moments vectorially, we will get the net magnetic moment. Now there is one more method called angular momentum method for the calculation of m. Let's say there is any uniform charge body, let's say hollow sphere, which is distributed sigma charge all over it. Then the angular momentum of this body is given by 2 by 3 mr square, and the and for this symmetrical case of this body, the magnetic moment can be simply given by this L, replacing this mass with the charge of this body. Let's say instead if I replace it with the charge Q and rotate it, if it is uniformly charged and if I rotate it, then we get a moment that is given by this L divided by 2 and mass replacing the Q charge. So it means 2 by 3 into QR square and dividing by 2. So L with mass replaced with Q divided by the total 1 by divided by the 2, that gives me the total magnetic moment of this body. That is called that is the angular momentum method, which we can use where L is given with mass, and this is the factor which changes the mass with charge, and the magnetic dipole forms similar field to electric dipole but in outside region only, not at inner axis. Okay, so these are some formulas due to the line charge and the electric field perpendicular to this line. E perpendicular is given by this k lambda by r, where r is the perpendicular distance, and sine theta 1 plus sine theta 2, where theta 1 is measured at one side and theta 2 is measured at other side. Means if I have a line charge here and I have to find the field at this point in this perpendicular direction, is E perpendicular, then in that case I will draw a perpendicular line, extend this line, and this length is, let's say, r. Then let's say this length is theta 1, the magnitude is theta 1, then this angle is, let's say, having theta 2 magnitude, then I have to take a minus theta 2 angle here, for because the angle is taken, one angle is taken in this sense and one angle should be taken in this sense. If both are coming in the same direction, then one should be negative. That's what I'm saying here. That's why I made these arrows here to tell the sense in which they have to be taken. This other formula is cos theta 2 minus cos theta 1 into and theta 2 kf direction. Means if I'm taking this theta 2 kf side before in this and subtracting the other side cos from this, then we have to take the n theta 2 kf, means in this direction, the direction which is in this theta 2 direction, I have to take that angle here, and the formula remains same, k lambda by r, k lambda by r. Only this part is replaced, and the direction can be think by logic also, and also the field at this point. This is the parallel field because it is parallel to the line system, and this field at this point can be also calculated by this formula because this is also a parallel field, but that would become very complicated to tell. Simply we can use this formula. This is the distance A and the total length is L, and this is A, so L plus A into KQ, that is the field at this point A. Similarly, in the magnetic field, we have only one formula, which is the field perpendicular. This field, let's say current is flowing in this direction, so here the field would be perpendicular to this plane upward, and that's why it is called B perpendicular. It is also given by this similar equation. Here we use the lambda, in this case we use I, so Ki by R, and same sin theta 1 plus sin theta 2 in the same sense as this. Now the field by the arc, by magnetic field and electric field. Here I take the arc having some theta angle, means the total angle of the loop would be 2 pi, but I am taking only alpha part of the loop, and on this axis there is a point here P at which is at x distance from the center, and at that point if I draw a line from this point to this circle circumference, that angle would be beta. So we can say that this length is of, if this radius is r, then we can say that r by x is equal to tan of beta. So in this figure, if there is some level of charge density or if there is some current flowing, this, let's say this is positive charge, so it will apply some force in this direction, opposite direction, while this current, if current flows in this direction, so V cross this R, that will apply some magnetic field in this direction and it will have some component in this direction. So that's why E parallel and B parallel are in this opposite sense. If the current was taken in this direction, that will go downward, and the formula is same. Both E parallel and B parallel have this alpha, and here we have k lambda by r, ki by r, just like we had here, but here we have radius and here we have distance, and we have sine cube beta in this case, while sine square beta, cos beta in this case, which is this angle. For E parallel, we have 2 sin alpha by 2, 2 sin alpha by 2, k lambda by r, k I by r. But here we have sin cube beta, and here we have sin square beta cos beta. Means these two parts here are replaced between E perpendicular and B perpendicular, P parallel. And similarly here, these two are same for this P perpendicular and E parallel. While the E perpendicular and B perpendicular have the same value of this alpha, means the alpha part is same for both of them. The beta part is exchanged, and this rest part is same for all four. And the E perpendicular equation has this graph, and the E perpendicular value is maximum. E perpendicular means the field perpendicular to this plane of the ring, which is along the axis, and the B parallel means in parallel to the plane of the ring. And this will be apply force symmetrically. The line which is bisecting this ring, and that line will be parallel to this. The field direction will be parallel to this line, and the maximum field occurs at the r by 2 distance. Similarly, in this case of, because we have, this is a constant thing, this E alpha is a constant thing, and only thing it is changing when we are moving along this distance, that is beta. So because sin square beta cos beta is for E perpendicular and also for the B parallel, so they both follow the same graph, and they both having maximum value at r by 2, so r by root 2 distance. The field value is maximum, while E parallel is maximum at the center and B perpendicular is maximum at the center. Now the next ones, the force is given by, electric force is given by the simply the electric field at the point into the charge, while the magnetic field is given by this kq v cross. Means if a charged particle is moving, it will produce some field given by kq v cross r cap divided by r square at field due to the charge q at r vector distance. And force is given by simply q v cross p. And force does not, field by on charge does not apply force on itself. Means if I am producing some field, then this field will not apply force. Field by a point charge will not apply the force on the point charge itself, but it can apply the force on other point charges. Now the Lorentz force is simply the sum of these two forces, total magnetic and electric force. And when we replace epsilon naught with E, mu naught with mu r, we are actually adding the effect of medium. Means when we are replacing E naught with E or mu naught with mu r, we are actually including the effect of medium, because the actual field by the charged particle is unaffected by the medium. The actual field by the magnetic field by the charged particle is not affected by the medium. But what happens is that the medium starts producing its own field, or if we place a charge in the medium also produces some charge. The charge gets induced in the medium, and overall the force due to the charge gets reduced on any body due to this induction. But instead of saying that medium is charged and it is applying force, we say that the electric field is reduced by the body due to the medium. In infinite charges, the field is given by the sigma by 2 epsilon naught at any side, and field by the charge, also the field by any sigma charge body, which is, let's say, a conductor. That field here would be sigma by epsilon, because Gauss law says that the flux would be, as we know, that it is q by epsilon, and because the total area is 4 pi r square, and 4 pi r square is the total area, and the total charge is sigma into the same area divided by epsilon naught. So we get the electric field that is 1 equal to sigma by epsilon naught in case of is conducting sphere, or sorry, conducting sphere. Now this v dq can be replaced with ideal vector. Means if we have any dq amount of charge which is moving, and it is some dl length, for example a current carrying wire in which we have any small dl length which has some dq charge, and it is moving with some drift velocity, then in that case this v into dq can be replaced with the I into dl vector. So in this case of magnetism, this velocity is a vector quantity, but we don't take the current as a vector quantity. That's why we use that's why we put the vector sign with the dl. And similarly for the infinite current carrying sheet, means let's say we have a sheet in which the current is flowing per unit length of the sheet. Let's say this is the sheet and the current is flowing out of the sheet, and this is length along it, so per unit length. So along this per unit length there is some I current flowing, and I am denoting this by, let's say, I lambda or lambda I, that is the current per unit length along the sheet. In this case the magnetic field due to this sheet above on any of the side would be equal to mu naught I by 2, which is similar to this. We get a 2 here, and the density, current density, and charge density. And because in electric field we get epsilon, in the denominator, and magnetic field we have mu in the numerator. So these two are in the opposite positions. So we can just use this equation to derive this by symmetry. Now the other formula is disk. When the disk has some charge, uniform charge, a disk is having some uniform charge sigma, and its radius is, let's say, r. Radius is not used here. Let's say it is having some beta angle, and at this point the field is acting in this direction, and I have to find the field at this point. Simply that would be equal to sigma by 2 epsilon naught bracket 1 minus cos of this beta angle, this is angle. So that A will be equal to this. And if instead this charge is rotated, the field produced at this point would be given by this formula, which is sigma k of the magnetic field 10 to the power minus 7 into pi by 2 omega r sine cube beta, where this k can be written as mu naught by 4 pi by 2 pi sigma omega r into sine cube beta, where this pi gets cancelled, and we get this mu naught upon 8 sigma omega r sine square beta. Overall, we can remember this formula: pi by 2 sigma omega, and the radius r means this radius r, omega, and sigma should be included, and this k is included, pi by 2, and this important quantity sine square beta, which is kind of similar to the field we calculated here, in which we get the field perpendicular to it when the current is flowing in this sense. We get sine square beta here. Similarly, we get sine square beta here. Now, electric field inside the hollow sphere, which is charged uniformly, electric field will be equal to 0. And if the solid charge sphere is used, the electric field inside it is rho r by 3 epsilon. Epsilon because the medium can affect the magnetic field, electric field value. And if we use it, sorry, this is another part, the electric field, in which if we have, let's say, any sphere is uniformly charged with sigma charge density. Now if I cut out some part of this sphere, then let's say this length from this and to this plane is, let's say, a, and this is the center, then at the center point the electric field due to this part would be equal to this angle is, let's say, theta, total angle is theta, then we get sine square of theta by 2 into pi k is sigma. Sigma is the charge density, k is the 9 into 10 to the power 9 sigma pi k sine square theta by 2, that is electric field at the center only, which is perpendicular to it. And this pi can be treated as the whatever, that is the formula. Also the solid angle is given by, if we have any angle like this portion, that this will have a solid angle, which is given by 2 pi bracket 1 minus cos of theta by 2, and the total solid angle of the space would be equal to, the full solid angle is given by 4 pi. The total complete solid angle is 4 pi, and the total 2D angle is 360 degree, which is 2 pi. And the area of this part, which can be also required in some questions, area of this part, which of this curved surface, that is given by this a distance a into r into 2 pi, that is equal to the area of this part, curved surface, given here. Now in the magnetic field, if I take a solenoid, means, let's say if I have a solenoid and I have wrapped some wire around it, and the current I is flowing in this wire, and I cut out some portion of this solenoid so that the current is still, means I am maintaining the amount of current in this coils, but I have taken out some portion of this solenoid, which is making some alpha angle, just like the ring case. So let's say that angle is alpha. Let's say that angle is alpha, and along this axis I am taking any point along the axis passing through the center. I am taking a point in this, which is making this theta 1 and theta 2 angle. It is similar to the line case, so we get sine theta 1 plus sine theta 2, and alpha is the angle of the solenoid cylinder which I have taken, and N is the terminal density, number of turns per unit length of the solenoid. And this formula turns out to be mu Ni when this L becomes very, very larger than the radius of the object. Means this two values becomes 90 degrees, and we get If I am taking the magnetic field at the center, and the length is very large, then we get this total value becomes 2, and we get this formula mu naught Ni, and the solenoid is taken complete where this alpha becomes 2 pi. Now in the solenoid, outside the solenoid, filled inside hollow cylindrical current carrying wire, okay. So if I have a current carrying wire which is current is passing through this cylinder's circumference, then inside this, and let's say the current is uniformly distributed, then the field inside this would be equal to 0. Now field at the center of a hollow charge which is rotating. Hollow charge sphere means if I am having a hollow charge sphere and that is rotating just like this case, we get this formula. I also have to memorize it. This formula, this one. So this formula is B is equal to pi by 2. So the formula becomes pi by 2 into k sigma omega and r into sine cube beta, where this field is perpendicular and it is rotating with omega, radius is r, field taken at this point. Okay, and if instead I take this shape and I found the electric field at the center which is perpendicular, that would be equal to, in this case, pi k, and sigma is a charge density which must be taken, and sine square theta by 2, where theta is the total angle. And the system hollow sphere is rotated, which is some sigma charge rotated with some omega, then we get again sigma omega r is again here just like this, but in this case we get the value turns out to be 2 by 3, in this case at the center, 2 by 3 times of mu into sigma omega r. Now one more thing, if we have any flat surface, then in that case let's say there is some field here in this space, and the field is producing some flux across, means through this section some flux is coming out, and that flux is, let's say, phi, and let's say this flux is external due to external fields. Means if I am taking any surface here and that surface is, let's say, charged, then that charged surface will also produce some flux through it. But if I ignore the value of, if I remove the value of flux due to this charge on this plate itself, and then let's say this is uniformly charged with sigma charge density, and I find out, if I can find the total flux due to the other charges externally, then I can tell the total force acting due to the electric field in this region due to the external charges F perpendicular is equal to this flux into sigma. Means this flux into sigma, that is equal to the total force on this body. But for a small part of this body, we can say that T phi is equal to sigma, that is the force acting on any small element on this surface perpendicular to it. Even so, in this case it doesn't matter whether the surface will obviously be flat because it is very small, but if I am taking a very large surface, we have to take a flat surface, and in that case the force perpendicular to the surface, that is given by the sigma charge density of this body into the flux coming out of it, which is due to the other charges. And we cannot use this method for, let's say, spherical body, for example this, because all the forces are okay. In case of solid sphere, we got the formula of rho r by 3 epsilon naught, but similarly in the case of uniform solid cylinder which has some current flowing through it with current density J, in that case inside this, if I take a r distance, the current flow will be given by this mu naught Jr by 2. So this 3 gets replaced by the 2 and epsilon naught gets replaced by the mu naught, and we get mu naught Jr field at any distance, and the graph looks like this. And that field formula for the solenoid is also the formula for the field of toroid. So of your there is no formula for the magnetic field. If there is a spiral current carrying wire which is uniform, means a current carrying wire is in such manner that it goes out like this and current I is flowing in it, and this is a center of it, let's say, and starting at a radius and it increases, and this end point is at some b radius, and the radius is increasing uniformly with the angle it rotates. And let's say the total angle rotated here in this case is alpha, which is this angle plus this angle, which means the total angle it rotated throughout the process, that is total alpha, let's say. Now in this case, for example, if I take this part, the alpha angle will be equal to this, and this is a and this is b. So in this case, the magnetic field is given by this: b is equal to alpha times of ki divided by the larger minus smaller ln of larger upon smaller. This alpha times ki by this radius ln b upon a. Okay. And outside the long solenoid, if there is a long solenoid, then outside it the field is approximately taken to be 0. Now a dipole, when it placed in a electric field or magnetic dipole in a magnetic field, the torque experienced by the dipole, that is given by this p cross c or m cross b. One more thing, that torque is calculated about a point, but because these are coupled torque, means there are forces with pairs in the opposite directions. In that case, the torque calculated about any point turns out to be the same. So that's why without giving any point we can tell the torque here. Torque is given by simply p cross e or m cross b, and m of the body can be, means in any kind of body, if we know the m and electric magnetic field, we can tell this is the m cross b is the torque on it. Similarly, p cross e is the torque on the dipole, electric dipole, and the potential energy is taken to be 0 at the reference 90-degree angle. Means if the electric field is pointing in this direction and the dipole is in this sense, vertical sense, then in that case we take the potential energy to be 0 at this reference point, and the potential energy when we rotate it from this state, that is given by minus p dot e, where p is the angle with the dipole moment and the electric field in its direction. Means let's say p is in this direction and dipole is in this direction, so we have to take this angle, and if the electric field is in this direction, we have to take this angle from this side. Now the flux is given by E dot d integration. The total flux is equal to total charge inside divided by the epsilon naught. We have to use epsilon naught here. Now one more thing about this flux, that is, if we have some q charge placed here and it is vacuum here, then in that case flux through this sphere would be equal to q naught by epsilon naught. But if I place a medium here, in this case the medium will produce some charge in it and the flux will become changed because the q internal becomes changed. But instead of writing this as q internal by epsilon naught, we can also write this as q divided by epsilon. The value turns out to be same, so q naught by epsilon, the value will remain same whether we replace q naught with q in or epsilon naught with e. The value will become same because we have to only divide by the k in this case, and the charge is decreased by the same times as the epsilon is increased. Now flux through the 3D closed surface is 0, and flux normally through the surface is integration of this. Potential energy is same for this also, minus m dot p. Now if we take a point charge and let's say there is a point charge q naught here, and let's say along this line I draw a disk here of radius some r radius, and this makes some angle theta with this axis, then in that case the flux due to this q2 charge that is passing through this surface would be equal to q naught by 2 epsilon naught bracket 1 minus cos of theta, where this theta is this half angle, or if I am taking the whole angle, then we have to take theta by 2. And this formula looks similar to this formula. And the energy of the electric fields store energy, and at any instant when the electric field strength in the medium is E, then that energy density of the electric field would be equal to E epsilon into E square by 2, and the medium affects the energy density. Similarly, magnetic field will store energy density is equal to B square by 2 mu, and the total energy can be given by the density into volume, energy density in the volume into the volume, and also this energy density is equal to the pressure due to this field on any charge sheet, or also pressure due to the magnetic field on any current carrying sheet. So let's say there is any charge sheet here and there is some field in this medium present, then the net field here that will give us the net energy density, and we have to use the energy density. This pressure acting at this side would be equal to, for example, this is the case with electric field here, E1 here and E2 here. The total pressure will be given by this E1 square minus E2 square epsilon by 2, which is the pressure from this side minus pressure from this side. This gives us the total pressure on this surface, where this electric field will be affected by the electric field due to this sigma charge plate also. And we don't need to know what is the sigma. If we know the value of E1 E2, we can directly tell the pressure on the sheet, and pressure into area will become the force. Similarly, the magnetic field case, we use the same method, pressure difference, and the net pressure will become the total pressure. And this is kind of a method to find out the total pressure, and that is very accurate method. Now the potential energy is given by the negative of the work done by the electric field, which is minus E dot dr integral. And if we are integrating from a larger value to smaller value, means if we are integrating with the dr but the distance is decreasing, means if you are increasing from 0 to some r value, then it would be a positive dr value, and we don't need to add any sign here. But if we are integrating it from, let's say, 0 to r, then in that case we need to add a negative sign in this case. Now one more thing in this case, the Ampere circuit law says that P dot dl closed integral in any loop, and let's say I take any planar loop, and in that plane, through that plane, the total current passing through this I effective into this mu, that gives us the P dot dl integral along this line in the plane. And this I effective is given by the IC plus IT, where IC is the total flow of the charge. IC is equal to simply dq by dt, the current due to the charge flow which is flowing through this plane from one side to the other, and the ID is equal to the displacement current, that is given by the total change in the electric flux, rate of the change of electric flux through this area, multiplied by the epsilon, where this can be written as A into E. Now these are some potential equations, like inside the hollow sphere, which is uniformly charged, potential is constant kq by r, while the outside the potential drops. And in this case of uniformly charged sphere, the potential inside is given by this 3r square minus r square by 2r cube, while outside it falls like this. And potential due to a small dipole at an large distance, that would be given by kp dot r cap divided by r square. And this is an approx formula, but if you want to find the exact potential, but I have the formula for the potential at the axis outside, means this is a dipole minus q plus q, then outside this dipole on this axis at any point p, I can find the potential by this equation, which is an exact formula, r square minus a square kp dot r cap, while in this case kp dot r cap by r square is an approximate formula for any potential at any point in the space. Now this is for the conductor and cavity, which can be read easily. One thing I will tell you that for the curved surface, the more curved surface have a smaller radius and they have higher charge density, means the more is the curve density. If I have two surfaces like this, then this will have more charge density, while this will have some lesser charge density. The more is the curvature, more is the sharp of curve. The more sharp curve is there, the more is the charge density. Now the capacitance, and that is given by this formulas, and energy stored is given by this. Now moving to this next part, capacitance is given by the total charge on the plate on any one part, magnitude of the charge divided by the potential difference across the plates for any parallel plate capacitor. But if we don't use a parallel plate capacitor, Then we have to take the parts of the body. For example, let's say we are having two cells, and one is storing plus q charge, one is storing minus q charge. Then the charge on one part divided by the potential difference across these two parts, we have to use this value to tell the capacitance. And now one more thing. Now let's say if I am having only one body, if I am having only one body charged, only one conductor, let's say it is charged with q charge, then in that case we have to assume that the other part is at infinite distance, and that is having minus q charge. Then in that case the potential at infinite distance would be equal to 0 due to this, and due to this also 0, because this minus q charge is spread in the infinite large size, that will have no effect at infinite distance. The potential would be approximately 0, would be 0 due to this charge. So the potential difference due to this is from infinity to this point. The potential difference due to this charge will be, let's say, v, and the charge stored is q, so we get q by v, where this v is the potential at the other end, other part 0, and v, sorry, delta v, where v is the potential at this part and 0 is the potential is. Now the total sum of the charges on the plates divided by the outer sides of these two plates means the total charge is, let's say, q net, then q net by 2 is the charge, and we can use the charge conservation to tell the charge at other sides. And if any one of the plates becomes ground, that means its potential becomes 0. Plates, we have to make sure, this is for the parallel plate only, that when we have any one plate at 0 potential, then net charge of the system should become 0. That's why I wrote here. In the case of a 0 potential, if any plate has 0 potential given in the system, then we need to make sure that the total charge on the system is 0, because we want to make sure that the electric field in the system becomes 0. So that if I bring a charge from the infinity to that plate, the work done becomes 0 due to the 0 electric field, because it says the potential is also 0 at the plate. And a charge can be treated like these capacitors, means this part can be treated as these two sides, these two parts, and one side of this conductor is participating as plate of the capacitor, and the other can be part of the other capacitor or can be just left as a wire. And this is the combination of capacitors. In parallel we have C1 plus C2 and so on, and in series we have reciprocals added. And one more thing, charging discharging of capacitors. Whenever we have capacitors, and let's say we are adding two capacitors together, in case of C1 capacitance, in case of C2 capacitance, they have charge Q1, voltage V1, charge Q2, voltage V2. Now if these two are added, let's say it is positive charge here and negative charge here. Now if these two are added together, then in that case we know that if the two plates are added in a manner, let's say their positive sides are added, then Q1 plus Q2 becomes the Q net charge on the combination, and the net combinations will be treated like a parallel plate capacitor, which will give the capacitance is equal to C1 plus C2, which is becomes equal to C net, and the total charge would be equal to Q1 plus Q2. But and also using this equation we can find the voltage across that combination, and if we add them in the opposite sense, means positive connected to the negative, then Q1 minus Q2 mode, that becomes the Q net. C net remains same, and using these two values we can find the net voltage across them, and using this we can find the energy changes of each capacitor and the heat losses also. The total final energy minus the total energy initial energy is equal to the change in the energy, which is equal to the loss of energy. Now here one more thing, few more formulas, that if we have two infinite line charges like this sq lines, which are mutually perpendicular and they are at some distance from each other, the force is given by λ1 λ2 divided by 2 epsilon. Means it does not depend on the distance between them. The force does not depend on the distance between them. It is a constant value given by this formula. And now one more thing, the image method. For example, let's say this is a conductor plate and it is grounded, means the potential at this conductor is 0. That is a very large plate, and I have placed a q naught charge at some L distance from it, and now I have to find the force on this charge on this plate due to this q naught charge. So to find this we use the image method, which says that we know that potential at this point at this plate would be equal to v is equal to 0. So to make sure that this is v is equal to 0, we can replace this plate with a minus q naught charge, and let's say this was the position of the plate initially, and at L distance we had the q naught, plus we have to just put a minus q charge at the other side, at L distance, and we will get this plane becomes the plane of this seed becomes the equipotential plane which has zero potential, and so this is satisfied by this minus q naught charge configuration, and the force on this force can be simply given by q naught square into k by the distance L. This distance is 2L, so 2L square. That gives the total force on the plate. When we place a charge q naught here, the charge will be distributed in this plate, and we cannot predict it how it will be distributed, but we can use this mirror image method to treat this whole seed like a point charge mass here. Means this whole seed will be like a point charge placed at this distance. And one more thing, that in this case of there is a, let's say, a ring here, and in a ring at the center the electric field is zero. All both parallel fields and the perpendicular field to the axis to this circle ring, the fields are zero in the center, but at some distance from the center in the plane of the ring, let's say at x distance, the electric field would be there, and that because we are using a ring and not a sphere, so in this case the field at this point can be calculated using the Gauss law. We use a cylinder which has same radius as this x, and we take some thickness t of this, and in this case, let's say this is the ring and this is the center, and about it we have at this point P at which we have to find the electric field, and we take a cylinder in this sense, and this length is, let's say, L, and this length is also L. So due to this ring there will be some electric field here in this direction which is very small. Similarly here we will get field. So because the total charge enclosed by this cylinder is zero, so the total flux would be equal to zero. So the flux due to this would be equal to the flux due to this field inward. So we get this equation, and using this we get this equation which is says that at very small distance, if we take a very small distance, then that was I'm saying near center, at very small distance the field is directly proportional to the distance. Now this is kind of an integral used. dv1 dv2 are the volumes in these two sections, equally divided sections of the solid sphere, and their integral, where this r is the distance between these two volumes, that is equal to this pi square r to the power 4 divided by 3. What is this actually? This is actually given by rho 1 dv1 rho 2 dv2 divided by r cube, this kind of integration, where this is the q1 q2 in these two mediums, and we have to integrate this value. So for if we fix one q1 charge, it will apply force on all of the q2 charges in this side, and similarly each of these q2 charge on this side will apply force on this side. So that's why we have to take this kind of integral, which is a very complicated, but we have this value of this integral. And when we have two lengths like this and a theta angle here, then this straight line length is equal to 2 times of L sin theta by 2. Okay, electrostatics and magnetism is over. Now the power in the devices. The thermal loss by the resistor is equal to I square R. Doesn't matter what kind of circuit you are using. The simple formula is I square R for the thermal loss by the resistor, if I is the current in the resistor and R is the resistance of the resistor, where R is the actual ohmic resistance, where, and if any device is having VD potential difference across it and the charge displaced across it is Q, then the work done by the device is equal to VD into Q. But whether this value would be positive or negative, this will be decided by the this VD value and the charge Q. Means, let's say we have a positive potential here by any cell, positive side is here, negative side is here, and if in any circuit, let's say from this side a plus key charge moves in this direction and a minus key charge comes into this direct side, then in this case, plus key charge moves out of this and it moves from this side and enters this side, then in that case, because the plus q charge was moved out of this positive side, we will say that the work done by this device is positive, and let's say the potential difference across it is Vd, so we will say Vd into Q is the work by this device, and that is positive also. But let's say the current plus q charge move into this positive side, then we will get vd into minus q work by this vd into minus q charge is the work by the device, that is actually the energy gained by the device. Now the electric potential energy stored of devices provides the potential energy, potential difference, and gives power given by, similarly the power given by the capacitor, sorry, this is the work done, and work done divided by the time dq by dt, that is the current. So for the capacitors the power is given by vci, and for the bed any device, for any device we can use vd into I to tell the power. For example, similarly, like here, if the current is going inward the power is negative, if the current is going outward from this positive terminal the power is positive for this body, means it is giving the power. So power given by the capacitor is given by VCI, power given by the inductor is VLI, and the sign will be decided by the current and the potentials. And resistors always consumes energy, it does not give any energy, so it always absorbs the energy, means it always does the negative work, which is given by this IR, and this can be given by a resistor with some current I in this direction. We get higher potential here, lower potential at this side if the current is flowing in this direction. So because the current is flowing into this side in this sense, so we can say that this is the positive terminal and this is the current going inward, so the work done is negative. So that's why the resistor actually takes the energy from the system. And if the capacitor is of zero resistance and it is, let's say, charged with a battery, let's say if I'm connecting a capacitor, uncharged capacitor with a battery directly with any switch, let's say I'm closing it and there is no resistance in the circuit, then the capacitor stores energy, let's say q charge is stored by it, then the total energy would be equal to q square by 2c by the capacitor, and the same amount of energy will be lost as radiation in the medium. But if we have any resistor in the circuit, the same amount of energy will be used by the resistors. Means if there is nothing in the system to slow down the current, then in that case the energy will be lost in the radiation. But if there is something that can slow the current, the energy, means if there is something in the circuit that can actually collide, that can actually take the kinetic energy of the particles, then in that case the energy will be lost by the resistance and radiation will not be considered in this case. If charge q is displaced at potential v difference, the total work is qv, the potential energy change is qv. And now I'm talking about inductor, and before that we have EMI. So in EMI we have two types of inductions of EMF. One is motional EMF and another is the Faraday's law of induction, which is caused by the changing magnetic fields. So one more thing we have to remember, that these two are very different type of things. Whenever we have a changing magnetic field, it means if the B is changing, then it will produce electric field. Means it produces electric field if the B is changing. But if the charged particle, let's say conductor, is moving in a magnetic field and the magnetic field is not changing, and the conductor is moving in the magnetic field, let's say, then in that case the charged particle will be acted by a force which is given by qv cross b, and this force is taken similar to the electric force applied on each charged particle. So this gives us the electric field equivalent, which is equal to v cross b. Means in this case, actually in motional EMF actually there is a magnetic force acting which converts the kinetic energy to the electrical energy, but this magnetic force is treated as the electric force. It is just assumed, not actual. In real there is no electric field here, and this electric field can be taken as v cross b. And while in this case of changing magnetic field, the real electric field is induced. And if we take a cylindrical region of magnetic field and the magnetic field changes in this region of cylinder, as circular loops of electric field will be formed with the same center as the cylinder. But if we take any weird shape of region in which the magnetic field is changing, we will get some weird shape of loops of electric field in this region, and the electric field will always form a loop, and this is a non-conservative force here, this electric field. in this case. Because of these loops, the particles can go round and round, and their kinetic energy will get increased and increased uh, with time. And doesn't matter whether you use this case or you use this case. The there is one formula which is d phi b by dt minus. This minus does not tell the sign. It only says that it is only used to make you aware of the Lenz's law, that is the magnetic field. The EMF will be in such a way that it tends to produce the current to oppose the change in magnetic flux. So that's why we use a negative sign here. It has nothing to do with the positive or negative value, and it can be removed from this equation also. It is just used to tell the Lenz's law. Now, after this, now in this case, when there is a moving conductor in a magnetic field, we have this formula for V cross B taken as the electric field, and E dot dl along the length can be integrated, and that gives us the electric field, which is simply V cross B taken dot with dl vector along the length. That gives us the EMF. While in this case of magnetic field, the magnetic field when changes, it produces some electric field, and we can write this dv by dt is equal to electric field dot dl integral. The magnitude of this integral is equal to dv by dt magnitude. So d phi b by dt, d phi b by dt magnitude. And for a cylindrical region of magnetic field, if it is changing, the electric field will also be circular with the same center. And you can read these cases. Now coming to the inductors. Ideal inductor has zero resistance, and the main property of inductor is to oppose the change in flux in the inductor. Means the property of inductor is not to oppose the current, but its main property is to oppose the flux, because you will see in some questions the main thing is to oppose the change in flux, not current. But if the permeability of the medium is fixed, then in that case the L can only be the flux can only be changed by the change in current in general. So that's why to oppose the flux, current is also opposed to change. And ideal inductor has no heat loss, and delta V is equal to, measured across the inductor, is equal to the potential difference applied to it externally. Or just remember that the potential difference measured across the inductor is taken to be equal to the potential difference across it applied to it, or the potential difference taken by the inductor from the circuit. And the potential difference inside the inductor is zero. Inside the inductor is zero. Because the resistance is zero, the electric field cannot exist inside the inductor. And in actual, we see that there is an inductor here, let's say, and inside it there will be some EMF in the back side. When the applied voltage in this direction, then the EMF induced will be in this direction. But it does not mean that the net potential difference across it measured would be zero. In actual, the potential difference measured is actually equal to the V applied. So V measured is equal to the V applied. Even though there is a back EMF, that is not what is measured here. But still there is electric field inside equal to zero. It is a complicated case, but just memorize this. So this is the thing, and V applied is equal to L di by dt in magnitude. They are of opposite sense. If the V applied is making this graph, then the EMF induced will be making this graph, so that the total sum of them will become zero at any instant. Now there are a few cases I have given, that when an ideal inductor is connected to a battery, as the switch is turned on, and now in this case what would happen? The EMF is equal to the V applied, which is constant. So V naught is equal to L di by dt. This is the magnitude, and we get di by dt is equal to constant. So the current will increase uniformly with time. In this case, when there is no resistor and a battery is connected. But now in the second case, charging inductor with some resistor in the circuit, means when there is some resistance. In this case, the I is equal to I naught 1 minus e to the power minus t by tau, where tau is called the time constant. Tau is equal to L by R for the inductor circuit, inductor and resistance, and tau is equal to RC for the capacitance and resistance circuit. And the peak values can be related like this: the EMF of the battery E by R is equal to I naught, and the graph of this I looks like this. Initially the current is zero and potential is maximum, and the potential decreases with time, and current becomes constant and the potential becomes zero. Kind of like this, maybe. So in this case, let's take one example for this time constant R value here. In this case, in this case of time constant L by R, where R is the resistance across the inductor of battery was short circuited. What does it mean? Let's take an example that we have a circuit like this, inductor here and few resistors. Now if this is short circuited, means let's say this battery has some internal resistance R, so we will include this internal resistance but remove the battery and short circuit it and have the same circuit as before. Now the resistance across this inductor AB, RAB, we have to calculate, and that would be equal to this R we have to use here. That is the same method we have to use for the capacitor resistance circuit with the battery, and the energy stored is Li square by 2, and the energy is stored in the magnetic form. Magnetic field is storing the energy in this case of inductor, and electric fields have the energy in case of capacitors. And now the third case, discharging of inductor. Let's say the current is initially I naught and it is discharging. There is some resistance R, there is no cell here. The system looks like simply this. Then in that case, we get this equation: I is equal to I naught into e to the power minus t by tau. The current drops and it takes infinite time. So this is the case of discharging, and this is the case of charging from the zero. So remember these two equations and this R method also. Now we have the capacitor. In the capacitor, charging of capacitor, ideal capacitor has zero resistance, and when we charge a capacitor, the charge, because initially when the battery is connected, the capacitor behaves like a short circuit and a large amount of current will flow, and then it will starts decreasing with time. Exact graph I don't know, but initially the voltage here would be zero and current would be maximum. In this RC circuit, the current is initially maximum and voltage is initially zero, but in case of inductor, voltage is initially maximum and current is initially zero. Okay, in this capacitor equations, we have to memorize this equation: Q is equal to this Q naught. Just like the equation for I, we have to memorize the equation of Q in this case, and differentiating this Q by with time, we can get the equation of I, and Q by C gives the voltage, and the time constant is RC, and that's it. IC naught is equal to E by R. Now discharging case is not given here, but can be simply derived. Like here we have this equation, writing this equation and solving it. Now there are some cases, if there are some capacitors arranged in the cubical form, then in that case the main diagonal will have the capacitance is equal to 6 by 5 C, the phase diagonal will have 4 by 3 C, and the edge diagonals will have capacitance 12 by 7 C. This can be understood by this can be also derived from the resistance, means not derived but memorized with the help of resistance. If there is cubical arrangement of this equal resistance, then in that case the minimum resistance is found between if two points AB are taken at the edge, and that is 7 by 2 LR, and if we are taking the face edge, that would be a little larger, which is 3 by 4 R, and if I take the main diagonal AD, then the maximum resistance occurs 5 by 6 R, and in the case of capacitance, this all value become reciprocal. So that's why we get 12 by 7, 4 by 3, 6 by 5. Now in the case of LC oscillation, which I told before, this is the analogy which can be used. L becomes mass, I can be treated as velocity, resistance can be treated as the BV in the case of damped oscillation. In this case of non-resistance circuit, we will avoid this, ignore this, and the capacitance is treated as 1 by K, where K is spring constant and Q is treated as the displacement. So we get this form of equation, and di by dt, and this di by dt is equal to d square q by dt, d square q by dt square, and because the I have taken the charge to be flowing from this side of the capacitor, and because the charge is decreasing on the capacitor but the current is taken positive, I have to take a negative sign here. So minus minus becomes plus, and this gives me the value of I naught is equal to omega q naught. Omega is equal to 1 upon LC root. And in this case, if I am starting with the current, if the charge was initially maximum, means if the system was started with fully charged capacitor, then we will get the q is equal to q naught into cos of omega t, which is maximum at t is equal to, which is maximum at t is equal to 0. And differentiating it, we get the value of current, and we get q naught into omega is equal to I naught. That is the case when if we started with the charged capacitor, fully charged capacitor, and the total energy is given by this q square by 2c plus li square by 2. And using this energy, we can energy and the value of q and I with respect to comparing them with q naught and I naught, we can find the phase also. Now talking about the AC and LCR circuits. So simply, when a sinusoidal wave is used, sinusoidal wave means if any wave with sine function, or if any voltage with sine function or cos function is given, or a current with sine or cos function is given, then it is a sinusoidal. It can be treated like a vector, and in that case, the inductor and the potential difference applied across inductor, or the potential difference across the inductor measured, that is equal to the, that is also a sinusoidal wave, and the capacitor also has sinusoidal wave of Vc and Ic. Resistor also gets sinusoidal wave of Vl and I. Means all of them will have voltage and current in sinusoidal form, and it will be pi by 2 phase ahead of I, and the resistance would be same phase with I, and the capacitor's voltage would be having pi by 2 phase lesser than the I. Now in this case, if the current is given in the cos function, then we have to use the VL in the cos function also. Means if I say that I is equal to I naught cos of omega t plus some phi, then in that case, if I measure VL, that would be given by VL naught into the same cos omega function, cos function omega t plus phi plus pi by 2. So if I use the sine function here, I will have to use a sine function here also and add the pi by 2. So that's how we will use it. And there is one graph for it, that the net current flowing is given by this vector which is rotating, and let's say this is omega t, and maybe let's say I is equal to, I naught, or let's say nothing. The I naught is here, and the I is having the magnitude I naught, VL is having the magnitude VL naught, VC is having the magnitude VC naught. Means all these sine functions or cos functions are having these magnitudes. The total voltage supplied to it has the magnitude VN naught, or the V source naught can be called V net or V source naught, and the VR across the resistors will be having the VR naught magnitude of potential difference. And the peak values can be written in these forms like XL I naught is equal to VL naught, and I naught Z is equal to V net naught, and I naught R is equal to VR naught, and actually VR is equal to IR, doesn't matter if it is peak value or not, and VC is equal to VC naught is equal to I naught X naught. One thing we should remember, that VL, the general values cannot be equated with this XLI, or XCI cannot be equated to VC, or IZ cannot be equated to VC, VS. Only their peak values can be written like this. While the resistance for the resistor, we can write this VR is equal to IR, it is correct, but this cannot be written. Only their peak values can be equated, because they are because they are not in the same phase. These are not in the same phases. Now this, let's say I am taking this angle in the anti-clockwise sense, this phi angle, which makes angle with this I, and the angle between this V and I, and this angle is going from this I to this V side, and this phi is given by XL minus XC by R, this XL minus XC by R in this sense, and cos phi is given by R by Z, and Z is given by R square plus XC minus XL whole square, R square plus XC minus XL whole square whole root. And if XL is greater than XC, we call it inductive circuit, and if XC is greater than XL, we call it capacitive circuit. And in the case of resonance, XL becomes equal to XC. In this case of LCR circuit, the XC should become equal to XL to get a resonance. And for any sinusoidal wave, whether it is cos wave or sine wave, we get this type of curve, and this type of curve from this peak value to this bottom value, if I take the average in this interval of this height, that will turn out to be 2 by pi of this height h, let's say h naught, and the root rms value of this height function along this interval would be equal to h naught by root 2 on the right. For example, if this is a voltage graph, we will get 2 v naught by pi and v naught by root 2, and the power average is given by Vrms into Irms cos phi, where cos phi is called the power factor, and this can be given by this angle here, R by Z, and the power becomes 0. Average power, this is the average power for the full cycle. If question is asking me the power for the any instant, I have to actually calculate the V into I, that is equal to P instantaneous at any instant. But if I'm finding the average value, that is equal to Vrms into Irms cos phi. These are some graphs like the XL increases with omega, and XC is inversely proportional to omega, and resistance does not depend on omega. And this is the resistance Z kind of thing, X or Z. Now these are called reactance, and this is called resistance. And now at omega naught value, the Z is minimum and the current is maximum. So the Z is minimum and the current is maximum. And if the resistance becomes smaller and smaller, this peak goes up and up. And when the resistance becomes 0, this becomes infinite here. And the graph looks like this at the omega naught value. And the bandwidth is the, let's say we took any value of current I. Instead of I naught, we are taking any current value I. And that current I is given at this, let's say the peak value of current occur at omega naught, and we are taking any omega I current which flows at this omega 1 omega 1 frequency, angular frequency. Then this difference into 2 times means this same thing will occur on both sides. Whether I decrease the omega or increase the omega, I will get the same amount of current. So the total difference is called the bandwidth. So the 2 times of this delta omega is called the bandwidth. And this bandwidth for a half power means for the half power, the current should be 1 by root 2 of the original value, and the current becomes 1 by root 2, or the power becomes half when the omega becomes some omega star, let's say, and the difference between them multiplied by 2 times of that delta omega, that is equal to R by L. And measure of sharpness is omega naught by 2 delta omega, that is bandwidth omega naught, which is the resonant frequency, divided by the bandwidth, is equal to the measure of sharpness of resonance, and the quality factor is given by Q is equal to 1 by R into root of L by C or omega L by R. And this value is this quality factor comes out to be the sharpness, means this omega naught by this value is equal to omega naught by 2 delta omega when the power is half, means 2 delta omega becomes equal to R by L. We get R by L, and omega naught can be written as 1 by root LC. So that's how we get this equation. And if now I have only told you the RLC circuit, now if we have to use the RL circuit or RC circuit or LC circuit with the AC supply, or so in that cases, then we have to get the equation of such cases, we have to just make that resistance or reactance equal to 0, which is eliminated from the system. For example, if the inductor from the LCR circuit is removed to make the CR circuit, means to get CR from the LCR, we simply make XL equal to 0, and XL is equal to omega L, and if L is not equal to 0, if omega is not equal to 0, we will say that L is equal to 0. And if LCR is needed to make the LR circuit, then in that case we will take XC becomes equal to 0, and we know that X is equal to 1 upon omega C, and to make it 0 we will take C is equal to infinite. So we will have to just make that component resistance provided equal to 0 to eliminate that part. If the resistance is removed and LC part is left, then we have to just take the resistance equal to 0. And there are 2 types of thing. One is if we have an LC circuit let's say capacitor and an inductor provided by some supply. That is one type of circuit, and we can also have another circuit with inductor and capacitor connected to each other. So for this case we have a different LC oscillation circuit which I told before. This is for the case when some V voltage is applied to it. Means this all cases are for this case when sinusoidal wave P or I are applied. Now the use of complex number method in this case of AC circuit. We know that the sine or cosine waves, sinusoidal functions, sine or cos functions can be treated as vectors, phasors, but division with a vector is not permittable. So that's why we use the complex number, because we can divide with a complex number. Now in this complex number, let's say the any quantity, any vector quantity is denoted by this z vector. Here this bar is not taken as z conjugate, we will treat it as z vector. Here we are not talking about any conjugate thing. Let's say this is z complex number vector. Let's say it can be voltage or anything that can be written as e to power iota theta or r cos theta into ir sin theta. Now in this case it is possible that our function is defined by this r cos theta value or r sin theta value. Means we can have a cos theta function, cos function or a sin function. So if our wave is given by cos function, then we can take this part of the function out from the z, or by after calculating the final value of z we can take out this part from the z, which will become our wave. Or if we are using the cos sine function, then we can find the value of z and take out this part, sine part. Means remove the I and this left part becomes our sine function of that wave required. Now we can treat this, and here we will use a notation like this. Let a z vector will be denoted by the magnitude of it, which is given by, let's say, z, and the angle will be denoted by this theta, where this theta is the angle with the reference frame, and reference frame is obviously a real axis and imaginary axis perpendicular to it. Now this reference axis, real axis, can be taken at any angle with the x-axis also. Means let's say this is the x-axis, and we can take real axis at any direction here, and the imaginary axis here. Means we can take the real axis reference at any angle also, and we can solve at that reference angle, and after solving all the values we can add this angle theta to our results. Means this theta to this final result theta, we can add this, let's say, phi value to get the reference with x-axis. And in general we solve the problem with respect to this omega t angle reference. Means we take a reference of this omega t, and the real axis lies at this angle with this x-axis, and we solve the problem in this frame, and the resistance is always along this real axis, and the xl is along this direction, and x is taken along this direction. Means xl is always at pi by 2 phase more than the with respect to this real axis. Means with respect to the reference frame, the xl will always be at pi by 2 phase ahead, and the xr vector, means these resistances or reactances, are also treated as vector in this case of complex numbers method. And the resistance is 0 phase difference with the reference frame, and x is pi by 2 phase behind the reference frame. Doesn't matter what is your reference axis, it will always be behind the reference axis with pi by 2, and xl will be pi by 2 ahead from this reference axis. And it is not dependent on the voltage, current, or anything. It is only dependent on the reference axis. Okay. And one more thing, in the case of the normal numbers, we were unable to write this vs is equal to I into xs, or vl is equal to I into xl. We were unable to write this, but in case of this complex number form we can write this. So congratulations, we can write this form. And we know that when we take product of two vectors, complex vectors, their angles gets added, and if we divide their angles, the angle in the denominator gets subtracted. And if we add two vectors, if we take add two complex numbers, they will be added like a vector, like triangles we use, they will be added like this, and magnitude will be multiplied if they are multiplied, and the angle will be added. So these things makes our work easier in the case of products of vectors. Now one more thing, we can use the voltage divider or current divider in the complex form. Let's say we have any part, device any part here with some impedance Z1, means it can be a combination of resistor, capacitor, inductor, can be any combination of it, and it has total Z1 impedance and this has Z2 impedance, and these all are given with respect to the reference frame. Means I am solving this problem with respect to the real reference frame, real axis here, and with respect to the reference frame, this Z1 is at some theta 1 angle, this Z2 is at some theta 2 angle, let's say minus, and this type of angles they have with respect to the reference frame, and we can solve with respect to this frame, and we can apply the voltage divider or current divider, but in this complex number form, that is voltage across this part in this phasor in this vector form, complex vector form would be equal to v into z1 by z1 plus z2. These are vector forms, and this z1 vector can be written as z1 and its angle with respect to this frame of reference. And let's say this reference frame is taken at omega t, then we don't need to add omega t in all of them, so it becomes easier to solve if we take any suitable reference frame, and similar equation is used here. And also remember that this z1 bar, this bar is not conjugate, it is just used to denote that we are using a vector, and z1 is used to denote the magnitude. Z1 is the magnitude, and z1 bar, this thing is used to denote the vector in the complex form. And the chapters are over. Let's say I will solve one question for you. Let's say we have a cell here, sorry not cell, AC supply here, which is given with V is equal to 10 cos of omega, sorry 40 plus, just a second, let's say the voltage applied by the source is equal to V is equal to 10 cos 4t minus pi by 4. That is the voltage applied by the source, and that source is connected to, let's say, a resistor here of resistance. This resistance is 100 ohm, and this is connected to, let's say, an inductor, and then a capacitor, and this capacitor is having 25 ohm. Let's say XC is equal to 25 ohm, and this XL is equal to 20 ohm in this circuit. So in this case, the omega is equal to 4, omega is equal to 4, and this is all the set, and it is asking me what is the V across this inductor, means the voltage across the inductor at T is equal to pi by 16. At T is equal to pi by 16, I have to tell what is the voltage across this inductor. So very complicated question. We can use this voltage divider in this complex form. So first of all, we know that some current would be flowing from this part, let's call this I1, sorry I, and voltage is V, and across this resistor the voltage is, let's say, VR, and then across these inductors the voltage is, let's say, VL and VC, and these two are actually VC and VL are equal, so let's call this voltage as V2, and the current through this is, sorry, let's say it's V0, and we have I1 current through this and I2 current through this, and total I current was flowing in it. Now in this case, first of all, the voltage, this voltage applied would be divided across them. We get the voltage across this L, or the V0 value would be equal to this total voltage applied dot this Z1. Let's say this total Z is Z1 divided by this Z is Z2, Z2 plus Z1. This is how we will get the voltage across this, means equation of the voltage across this, and we know that we have to use a complex form. In this case, we will use the reference frame of the 40. So if I sit on the reference frame of 40, the voltage becomes, with this cos function, this phase becomes minus pi by 4. So means with this reference frame, the voltage is at actually pi by 4 or 45-degree angle behind. This is the voltage of the source, and the this is Z1 which is equal to 25, 20. These two are parallel, so the Z1 1 upon Z1 will be calculated as 1 upon the XC plus 1 upon XL. So in this case, with this reference frame, we know that the x is above, xl is above and x is behind. So we can say that it is, this can be written as 1 upon xc with minus pi by 2 angle plus 1 upon xl at plus pi by 2 angle, that is giving me the z1. And this xc and xl values are known. This is 20 and this is 25. So this angle goes above and it becomes plus pi by 2. This angle goes above and becomes minus pi by 2. And because these two are in the opposite directions, I can simply subtract one of them. So I will get, let's take the common angle to be pi by 2 plus pi by 2. So I will take a negative sign here, 1 upon xl and 1 upon xc. That becomes equal to, this is 25 and this is 20. So we get 25 into 20 and 20 minus this 25, that is equal, and with this plus pi by 2 angle, that is equal to, that gives me minus pi by 25 into 20 at this pi by 2 angle, that is actually equal to 1 upon 100 at minus pi by 2 angle with this reference. So from the reference I can say that this z1 is actually the reciprocal of this, z1 vector is actually the reciprocal of this given by this plus pi by 2. So the z1 is found out, and now I have to take the sum of this z1 and z2 vector. I know that z1, z2 is in the along z2 makes 0 angle and z1 makes 90-degree angle, and both are of 100 magnitude. So then net would be equal to root 200 and that would be at 45-degree angle. So it gives me, so I can say that the z1 bar divided by z1 bar plus z2 bar, that is equal to, the z1 bar is actually equal to 100 at pi by 2 angle divided by this will be, the result would be root 2 times of 100 and the angle would be pi by 4. Now this pi by 4 goes above and we get 1 upon root 2 and pi by 4 gets subtracted and we get pi by 4. In this question, this whole value turns out to be this, and so it means the V O is equal to V into 1 by root 2 and multiplying by this angle pi by 4, and because this angle is actually pi by 4 behind and means it is having minus pi by 4 angle and we are adding pi by 4 angle to it, so overall angle becomes 0 and we get V naught by root 2 at 0 angle. This is the magnitude, sorry, this is not V naught, it is V. It is V at 0 angle divided by root 2, and I have removed this bar because now it is a magnitude here only. So in this case the V naught function is given, maybe I'm doing any mistake, 100 and 100 will give me root 100 and the signs are okay. This is xc plus xl and this xl is having plus pi by 2 which becomes minus pi by 2 here above and it becomes plus pi by 2, and I subtracted this, so this becomes negative here, so we get 25, 20 minus 25, and so all of these values would be, seems like correct. So this was at pi by 2 angle here and we get pi by 4 angle, and the x, this voltage applied here, sorry, with the omega naught t phase reference, if I say with respect to this 40 reference, the voltage was at this angle, and I found out that this voltage VO should be at this line at the reference, and in this case it means the V across the device is along this line and the V applied is this. Okay, let's try to complete it. The function of V was given to be minus pi by 2, sorry, the magnitude of that was 10 and that was given with respect to reference frame. We got this value with respect to reference frame, but the reference frame is itself at omega t, sorry, cos omega t we need, means we need to add omega t angle in this case, to get to the original reference means at the x-axis, because the real axis was taken at the 40. So we have to now add this 40 angle in it, and the real axis will now come to this x-axis. We get this v vector like this: v naught is equal to this tan by root 2 into some cos of omega 40. And if the time is equal to, let's say the time is given to be pi by 16, so we get pi by 4 here, and cos of pi by 4 is simply 1 by root 2, so we get 10 by 2, which is equal to 5 volts. So the voltage across these 2 points at pi by 16 time t is equal to pi by 16, that would be equal to 5 volt. Correct answer. So we have to just use these wisely properly, the parallel sums and how the angles would be added. That's it. Bye bye. Goodbye.